Good day to all of you. Myself, Dr. Arvind Sharma, Associate Professor in Physics, Government Dungar College, BKN. Today we are going to discuss the solution of quantum harmonic oscillator using Schrodinger equation. In your M.Sc previous, the solution of quantum harmonic oscillator is using Schrodinger equation and by using operator method. There are two kinds of different methods. This Schrodinger equation method is same as you derive in your UG class, but operator method is new. But both questions are important for your this class. So let us start quantum harmonic oscillator using Schrodinger equation. This is a very good article written by Rachel Dudick. Solution of harmonic oscillator using Schrodinger equation. The solutions are given in your book. Some notations should be different, but maximum things are similar. And this is very good article written, and you can understand the conceptual basis also. And at the end of this article, few numericals or conceptual questions are also given, and that is also useful for your NET examination. So initially it is given abstract what is given in this paper. Harmonic motion is one of the most important example of motion in all of physics. Any vibration with a restoring force equal to Hooke's law. If restoring force is equal to Hooke's law, is generally caused by a simple harmonic oscillator. The potential for the harmonic oscillator is the natural solution, every potential with small oscillations at the minimum. Almost all potentials in nature have small oscillations at the minimum, including many systems studied in quantum mechanics. Here, harmonic motion plays a fundamental role as a stepping stone in more rigorous applications. In this topic, harmonic oscillator is characterized by Schrodinger equation. This equation is presented in section 1.1. The harmonic oscillator has only discrete energy states, as is true of one-dimensional particle in a box, like as one-dimensional particle in a box. The equation for these states is derived in 1.2. An exact solution of harmonic oscillator problem is not only possible but also relatively easy to compute given the proper tools. It is one of the first applications of quantum mechanics taught at an introductory quantum level. Systems with nearly unsolvable equations are often broken down into smaller systems. The solution to this simple system can then be used on them. A firm understanding of the principle governing harmonic oscillator is prerequisite to any substantial study of quantum mechanics. These are the contents. Solution of the Schrodinger equation, the Schrodinger equation of the harmonic oscillator, the power series method, math moves and helpful hints, solved harmonic oscillator problems. Solution of Schrodinger equation. The classical potential for a harmonic oscillator is derivable from Hooke's law. It is conventionally written Vx equal to half kx square, where omega is the natural frequency, k is a spring constant, m is mass of the body. Omega equal to under root k upon m. For convenience, in this calculation, potential for harmonic oscillator is written Vx equal to half m omega square x square. Okay. Placing this potential in the one-dimensional time-independent Schrodinger equation, this equation becomes d2 psi upon dx2 plus 2m upon h bar square minus m square omega square upon h bar square x square psi equal to 0. This is the equation for quantum harmonic oscillator. Is a second order differential equation that can be solved using power series. In the following section, the power series method is used to derive the wave function and the eigen energies for the quantum harmonic oscillator. The first step in power series method is to perform a change of variable by introducing the dimensionless variable y. Y equal to under root m omega upon h bar square h bar x. Using this equation becomes Schrodinger equation becomes d2 psi y upon dy2 plus twice e upon h bar omega minus y square psi y. For very large value of y, the term 2e upon h bar omega is negligible in comparison to the y square term. With this fact, we can guess that y will be as e raised to minus y square upon 2. E raised to plus minus y square upon 2. A general solution to the differential equation is, some mathematical term is missing here, but you can easily understand it by lecture or by using your book. Psi y equal to uy e raised to minus y square upon 2. Minus y square upon 2 is solution is acceptable here. Plus is not acceptable. We must now calculate the derivative of psi that will be substituted in the equation. This equation becomes d psi y upon dy equal to this term. And double derivative you can easily calculate. Okay, putting the values from equation 8 and 9 in equation 7, this equation becomes equation 11. Cancelling the terms, the math is very easy, you can easily do, and these steps are in given your book clearly. Cancelling terms and dividing through by e raised to minus y square upon 2, we obtain this equation. This equation is d2 uy upon dy2 minus 2y du upon dy plus 2e upon h bar omega minus 1 uy. And function is uy that we define. The next step is to solve the second order differential equation 13 above for uy so that we can find an exact solution for uy. We begin by using a power series of y as the general solution of equation 13. Uy then takes the form below, uy equal to summation 0 to infinity alpha n y. Alpha n yn. In order to substitute this solution into equation 13, we have to solve the first and second derivatives of uy. So you can easily compute these according 15 and 16. Replacing uy in 13, we have this equation. Simplifying the second term, replacing n with n plus 2 in the first term. Okay, for this discussion, this substitution and simplifying, we have these steps of maths you can easily do. So do these steps. We can then solve for alpha n plus 2 because the coefficient for each power of y must equal to 0. For each coefficient, power of y must equal to 0, right hand side of equation 20. Alpha n plus 2 equal to 2n plus 1 minus 2e upon h bar omega upon n plus 2 n plus 1 alpha n. Equation 21 is a series representation of all the expansion coefficients in terms of alpha 0. For the power series solution to equation 13, for large values of y, n is also very large. The ratio of alpha n plus 1 and alpha n from formula 21 of the coefficient of the power series expansion above is very close to 2 upon n. Here we have a problem because in the limit 2 upon n grows faster than the exponential term in psi y. The series must terminate in order for our solution to have any physical meaning. The best way to terminate the series is to equate the numerator in equation 21 with 0. We have twice n plus 1 equal to twice e upon h bar omega equal to 0. We can solve for e and we have the solution e equal to n plus half h cross omega. We have found an infinite number of energies for each energy level n. The formula for the wave function is incomplete, however, because the power series solution is incomplete. The individual eigenstates of the Hamiltonian must be made orthogonal. Harmonic polynomials need be incorporated into the final solution in order to do this. If we want to exact solutions or good solutions, we must incorporate Hermite polynomials into the solutions. What results is a function of the form psi x equal to m omega upon pi h bar raised to 1 by 4, 1 upon under root 2 raised to n factorial n, bracket m omega upon h bar raised to half x bracket close e raised to minus m omega upon 2 pi. The following is a table of the first 5 energies and eigenstates for the harmonic oscillator. Okay, this is minus m omega upon 2 h bar x square. Okay, so you can easily understand how the different orders eigenfunctions and eigenvalues are here. First order eigenfunction is psi equal to alpha 0 e raised to minus y square upon 2 is many times used by you in your numericals. Math move and helpful hints. Here different steps of mathematics is given, how expansion is given and how you can use. This is also important for you. Hermite polynomial. What are the Hermite polynomials? You studied these kinds of polynomials in your mathematical physics, different kinds of polynomials. Hermite polynomial is defined as the solution of Hermite's differential equation. This polynomial is a direct result of solving the quantum harmonic oscillator differential equation. The Hermite differential equation takes the form d2y upon dx2 minus twice x dy upon dx plus 2ny equal to 0, where n is a real non-negative number n equal to 0, 1, 2, 3. Hermite polynomials form a complete orthogonal set on the interval minus infinity to plus infinity with respect to the function ey. The orthogonality relation can be shown integral minus infinity to infinity e raised to minus x square hmx equal to 0 if m not equal to n and equal to 2 raised to n factorial n under root pi for m equal to n. With the orthogonality condition made, piecewise continuous function such as the solution of the quantum harmonic oscillator can be expressed in terms of the equation for Hermite polynomials. Summation n equal to 0, Cn Hnx equal to fx, where fx is continuous, and equal to fx minus 1 plus fx plus upon 2, where fx is discontinuous, where Cn equal to 1 upon 2 raised to n factorial n under root pi integral minus infinity to infinity e raised to minus x square fx hnx dx. Hermite polynomial is graphed below. Hermite polynomial graphs for different orders is shown in this graph. Okay, so we understand about the solution of the harmonic problem. The Schrodinger equation for the one-dimensional harmonic oscillator is reduced to the following equation for the polynomial Uy. Determine the recursion relation separately for even and odd states. Derive an equation for energy for both the even and odd states from the recursion relation above. Find the first three energy values from each of the equation obtained. So steps are given here, so you can easily understand it and you can do it. Similar method, alpha n plus 1. Now E equal to h bar omega 2n plus half for even state and h bar omega 2n plus 3 by 2 for odd states. And other parts you can easily do from here. Find the energy levels of a particle moving in a potential of the shape Vx equal to infinity for x less than 0 and Vx equal to m omega square upon 2 x square x greater than 0. Okay. So you can do these things easily. The given onwards, do these things yourself and you can easily understand. These are the references from this article is written. Some papers, books, famous books and papers from this article is written. This is the very good article, so I prefer this article for the lecture. So first of all, read this article carefully and try to understand and compare this article with your book. There is some parts of maths is not given here that can be you can easily understand by your book because you already done it in your UG class. So concepts from this article that is very useful for you and try to understand this. Okay, in next lecture we do this the same problem for harmonic oscillator using the operator method. That is very important for your M.Sc previous class. Both questions are important. So if any question is given in your examination, so first of all read it carefully, that is using Schrodinger method or that is using operator method, because both questions are different. Okay, thanks to all of you.